First of them, I just wanted to complete a thought that we had started last time, surveying innovation for the course. You recall that I had previously described the rationale and motivation for looking at data science from a software engineering perspective, noted some characteristics of big data, particularly concentrating on the 4 V's, the volume, variety, velocity, and veracity. I had noted some of the data sources that we'll be using in the course of the semester. Now, data science exhibits not just intriguing analysis potential, but it exhibits needs that challenge traditional software engineering paradigms. The first and foremost of them is the need for scalability in terms of data science, and this involves scalability in terms of processing small amounts of data and large, but also involves scalability from sort of very interactive interaction with programs on the one hand to rigorously tested sort of industrial strength analysis mechanisms that can run on a routine basis. And in trying to understand why Scala addresses these needs, I noted some features of Scala, some of which we've seen glimpses, and some of which we'll see more today in the exercise. But many of these will follow us through the chapters of the book and follow us through the course here. Now, more than that, I noted that many of these features of Scala that we're going to be talking about inherit from this general paradigm of functional programming. Functional programming being a paradigm that supports equational reasoning about programs, performs programming tasks with minimal side effects, and that has particularly notable support for modularity, clear error handling, clear dependencies, which can support parallelization, and very nice support for asynchronous ability and for sort of orthogonal higher order functions that can be used in a wide variety of contexts that are quite different, but use the same underlying mechanisms. And more than that, it has a kind of natural match to the analysis workflow. Now, these are features of functional programming. Scala as a language has some notable features that support scalability beyond these, such as its use of compiled language, supporting catching a lot of errors statically at compile time, and support for both sort of higher level constructs in functional programming, such as monads, while allowing us to interoperate with code bases in other languages, namely those based on the JVM, the Java Virtual Machine, and notably including Java. And it does have a very nice read-eval print mechanism in the form of the Scala shell. And that's mirrored in the shell that we're using in the course of the class based in Zeppelin. And for the first part of the class, the sorts of exercises that we're talking about can be pursued either in that shell, or it can be pursued in the context of, in other words, it can be examined in the context of the Scala shell or in the context of Zeppelin. Either actually will work very well, and I'll be giving a glimpse of the Scala shell in case any of you want to pursue that in just a few minutes here. Okay, so I'd like to talk now to sort of close out this assignment or this first lecture, I'd like to talk about Spark, because Spark will be a platform that we'll be using centrally throughout the latter 2/3 of the course. And it's important to understand why we're using it, and just a little bit about what its motivation is. So Spark is a platform for distributed, that is in a form of cluster computing, and it's targeted strategically towards data science. So Spark is a platform that was created in many ways to meet the needs of effective, scalable data science. Many of the same desiderata that are addressed by Scala, particularly this need to go from sort of scripting-like exploration to large-scale pipelines, the ability to handle things with limited memory and huge amounts of data, the ability to process things in a parallel fashion. Those all play a big role in Spark's design. The goal here was to move beyond a situation which had bedeviled researchers previously, where we had very different environments pursued for different types of analysis tasks without a sort of common base, a common infrastructure for them. So you'd use very different tools for different tasks. And it led to a kind of cacophony of different tool sets, different languages, different requirements that data scientists would have to pursue in the course of a day. They might use very, very different tool sets because no one tool set had the requisite generality to handle a large number of different analysis needs and the ability to scale out and scale up, etc. So generality is a big component of this. Spark is a platform that does support many types of tasks, and almost as important, in my view, is it's a platform that supports many particular variants of an interface for it. So it supports Scala, it supports Python, it supports R, and these can make use of kind of common underlying mechanisms. But its native language is Scala, and that's part of the motivation for us concentrating on that. But it's also a reflection of Scala's strengths. Now, beyond this, it put a strong emphasis on performance. And the reflection here that I like to offer is that that when it comes to data science, like dynamic modeling, we learn much more quickly and effectively if we can undertake experiments in an interactive way. If we can undertake them in a way that doesn't take days of runtime, but if we can undertake them in minutes, hours, or ideally seconds, we can often refine our thinking much more quickly. We can learn much more quickly. And like dynamic modeling, data science has a key need for this learning, because often you are conducting analyses and you're not sure upfront which strategies will bear out, which will work more effectively, which will be more desirable solutions. And like with dynamic modeling, you're learning as part of that process. So performance is a key need here. Performance in order to enable this sort of learning. And it has this kind of common stack. And by common stack, I mean a common set of technologies which, regardless of whether you're using a logistic regression model or an artificial neural network or a decision tree or decision forest model, whether you're using a model that's based on a number of additional machine learning approaches, you can do that all in the same platform. You can process data in large amounts in that platform. You can process text data as well as numeric data. And these all make use of kind of a large set of common mechanisms. And this allows the people who conduct data science to really update one system versus many very different systems for different needs. As I noted, it provides cross-language support, and it supports a wide variety of mechanisms for bringing in data. These include everything from CSVs to SQL databases to NoSQL databases such as Cassandra, which we'll be using quite a bit, files on the Hadoop file system, etc. And different of those data sets or different data sources offer different advantages. It also has within the platform some semi-specialized components such as Spark Streaming for things that involve incoming data over time, such as Twitter, live Twitter feeds, for example. You could think of data coming in via Ethica in this context, where you have data arriving over time and you want to process it live. And it has this two machine learning libraries, what's called ML and what's called MLlib, not to be confused with similar language names. And then there's GraphX for graph processing and Spark SQL. And there's a rapid evolution that's gone on within Spark that we will be likely encountering for some of its implications in the course of the semester. So these are characteristics of Spark, and we're going to be running an environment that uses Spark. And in fact, what I've already asked you to undertake here is something which is using Spark. So these mechanisms here that we're going to be using in Zeppelin are running by default on what's called the Spark shell. And the Spark shell is a shell that is used to interact with Spark. And in fact, the commands we're executing here secretly are in Spark. Okay, now a few more words about Spark. So Spark elicits great performance advantages from its design, which was very consciously designed to support eliciting those, securing those. Now, there's two particularly big areas where Spark shines. Two areas where I view it as gaining a lot of its advantages because of these characteristics. One of them is the capacity to execute distributed programming. So the idea is, just like the farm of machines lines behind you, you could literally command hundreds of machines or thousands of machines from a single query and have them in a semi-intelligent way divide up the data, process it, and get results back to you. And do that in a way that's transparent, that you can easily think about, easily reason about, etc. Not in a way that requires a lot of cryptic programming that has to be done just for your problem, but rather something that makes use of these general mechanisms, this common stack. Regardless of whether you're doing a artificial neural network or whether you're doing a logistic regression model or what have you, or a simpler data processing task, you can use the same basic mechanisms. So that distributed processing is powerful, and it's particularly powerful because it can be iterated very quickly without long periods of programming between. The second major component is memory conscious computation. So much of Spark benefits from something that Scala helps provide us, to wit, the ability to execute complex pipelines with minimal memory footprint. To minimize the amount of data that has to be loaded at any one time. And there's many reasons we get this in Spark and in Scala. One of them is the laziness of the language, which seems a total non sequitur. Like, why is laziness, this ability to defer computation, have anything to do with how much memory you use? In fact, you might think it uses more memory because you defer things. You have to remember, I'm still waiting to do this. Well, it turns out it has everything to do with memory, and we'll be exploring why that is in a later chapter of the book. Secondly, things are immutable in Scala and Spark. Typically, we execute equational, we execute code that's amenable to equational reasoning because it's side effect free. We perform computations based on some data we read in, and we perform a series of steps on it, and we get some result. And that has the characteristics that it's functional. There's no side effects where what we're doing can be characterized equally so by the results or the computation that gave rise to the results. It's not like if we run the computation twice, it gives different results. And one can substitute for the other. And what this means, amongst other things, is that we can, when we have data, because it's not being mutated, we can share it. We can have many different things referred to that same underlying data, work off that data, because they don't have to worry that it's going to be changed out from under them, that it's going to suddenly change, and therefore, to avoid someone changing it in another part of the program, they have to make a copy of it. We can minimize copies because it's not going to change. We know that. But equally much so, we can keep track of the provenance, the lineage of the computation, where this came from. What was the whole computation that gave rise to this? And if we're getting short of memory, we can get rid of what we've computed thus far and just remember how to recompute it if we need it. Instead of keeping around the full result, we just know how to go get it if we need it. So we can trade off computation now with computation with memory. We can recompute something if it's pretty quick rather than keeping it around in memory. We can discard it, in short, with the complete confidence that it can be recreated. And this provides a sort of flexibility in managing memory that's not unlike what you get with caches. If for those of you familiar who have taken 215 or other classes which deal more with lower levels of computers, right? You have a cache that keeps things in memory, in fast memory. We have a memory hierarchy with computers. You have successive levels of faster memory, and typically you cache things that are frequently used in the fastest memory, but if you have to discard them for something that is going to be used even more, you can do so with the confidence you can go get them. You can go get them from a lower level of memory. So we keep things in the memory of the computer rather than on disk, but we can toss things away in the memory of the computer. We swap them out and keep them on disk when we need them. Or we have level 2 caches or level 3 caches with processors, and it's like that all the way up. And it's a similar concept here. We can swap things out or swap them in. We can recompute them, etc. Another thing is, it turns out that Spark allows us, and we'll be seeing this a bit, to specify aspects of memory constraints. We can actually consciously say things about how to partition our data, how to divide it up in an intelligent way, to assist the speed of the computations, to assist in dividing them up in a judicious way, a savvy way across machines, and to minimize what's called shuffling, where we have to bring together data from two different places and combine it and to get further processing of the data. It's really nice if we could divide it up, have it chunk away independently for a long time without having to bring data from one to the other. And we'll be talking about this in its relationship with what are called partitions. So a few important concepts for Spark: immutability, provenance or lineage of data. Where did it come from? How do I compute it? How do I compute it again? Spark's basic mechanisms: resilient data, distributed data sets, so-called RDDs, and their close cousins but more refined versions, namely data sets and data frames, basically keep track of where the data came from. So if we need to discard it, we can do so and get it back by recomputing it. Laziness. So this notion of laziness that we see writ large in Scala is revealed in Spark. And we have this distinction in what are called transformers versus actions. So there's some things that just kind of transform data as part of a pipeline to get you along the way. So maybe it's something you take a corpus of data and you strip out, the first transformer strips out stop words, sort of words that are not particularly significant. A next one does stemming, so it turns verbs and gets rid of all the different conjugations of the verbs that are the bane of many Indo-European languages, right? You have a given verb, and you have these different conjugations of that. I am, they are, I was, I am being. Horrible, isn't it? So you might have that as a transformer. Then you might have a transformer that further goes and removes punctuation or something like that. Those are transformers. They're just steps along the way. And typically when you undertake a transformation, you don't actually apply it. You reserve it to be applied later in a memory sipping way. And then you have some things that require the data. For example, there might be something that what it does is based on the contents of the data. It can't proceed without knowing something about the contents of the data. So then it forces it to be computed. We saw a little bit of that last time when we were working with streams. There were certain things we did that forced it to say what was in the stream. There's other things that we were doing that would just produce another stream. And it actually didn't compute it along the way. We'll probably see more of that today. So Spark, memory consciousness, very conscious about the memory hierarchy, and distributed computations, partitions, and shuffling. Implicit conversions between data types. This provides us a way of having rigorous type-checked, rigorous computations, but at the same time getting a tremendous amount of convenience. We'll be seeing some things with key-value pairs with data sets and type safety in the form of data sets and their ability to capture concepts which many of you know from Python or from R or other contexts, this concept of a data frame, which is kind of a tabular structure where you have a set of columns of data, each with a nice name, and there's a defined number of rows, which applies to all the columns. This is a common concept if you've worked with large data sets in packages like R, probably, because it's quite fundamental and it's very useful, and we'll see those within Spark. Okay, so these are some important concepts, ladies and gentlemen, within Spark, and concepts we'll be exploring in the course of the semester. Are there any questions about this before we dive into a discussion of exercise 1? Questions? Okay, so what I'd like to do now is to go into exercise 1, and I'd like to talk about the challenge that I offered and the solutions to those challenges. So what I'm going to do is I'm going to save